Welcome to a lesson with Dr. Powell. Let's take a look at an idea called matrix multiplication. You see this array of numbers down here? This is a matrix. This is another matrix. Another one, and another one, and another one. They usually have parentheses around them, or sometimes they have brackets around them too. Okay, so what do these matrices represent? And there's an operation between them. What does this represent? Here's an example. Let's suppose we have two expressions in three variables. And these expressions are arranged or written down in such a way such you have x's, then y's, then z's. And you're simply just multiplying the x variable by a number, then adding a number multiplied to the y variable and z. We could represent this expression right here, 2, 3, 2. Thinking of like terms, the x term, the y term, the z term, similarly for the other expression. So we can have a matrix representing, which is just an array of numbers, which represents two expressions. Now, this operation here, it looks like multiplication, but actually, if we were to write composition or like an open circle, that would be a little bit closer to the truth. We say matrix multiplication, but really what we mean is plug in. So we're plugging in something here into these expressions. What we plug in here, we write down in a column. So the first matrix in a matrix multiplication could be thought of as the expression matrix. The next matrix over here can be thought of as the input matrix, which represents inputs that you're plugging into your expressions. The expressions are always written out in rows. The inputs are represented in columns. In this particular example, there's only one set of inputs being plugged in, but it's put in as a column. So there's a difference between these two matrices, and it's important to know which order we're writing things down when we deal with matrix multiplication. Just like it's important for order when we do function composition. It's the same thing, which also represents the same basic idea of plugging in. So this matrix, the input matrix, we think of its columns, and the expression matrix on the left, we think of its rows as being expressions. So this 1, 2, 3 literally means x is 1, y is 2, z is 3. Then what should the output of this operation be, which right here represents something we call matrix multiplication, which really can be thought of as plugging in operation. So a plugging in operation, what happens? Well, it's plugging in. You basically plug these values, x is 1, y is 2, z is 3, into both expressions. You plug it into the top expression, the first expression, see what happens. 2 times 1 plus 3 times 2 plus 3 should give us 11. Plug these values into the second expression. 1 minus 2 plus 6 should give us 5. Hence, the result of this operation between matrices, this input operation, is simply 11, 5. Next, let's look at the same example, but let's give ourselves another input column. So this column represents the inputs, x is 1, x is 2, and x is 3, just as we had before, and we plug those into each expression individually, and we should get out 11, 5. Just as we did before. But wait, we have another set of inputs. We plug these in to both expressions. So 2 times 0 plus 3 times 1 minus 1 gives us 2. Plug it into the next expression. 0 minus 1 and then minus 2, so give us negative 3. Notice the way we arrange the outputs of this plug-in operation. The rows represent which expression we were plugging into. So everything in the first row represents the outputs that come from expression 1. Everything in the second row represents outputs that come from expression 2. Everything in the first column represents, well, we were plugging in things in the first column of the first input column. So the first set of inputs, or x is 1, y is 2, and z is 3, is what we were doing to get the outputs here in our expressions. That's how we get this first column. This column over here comes from the second set of inputs, taking those and putting them into the expressions. So the output matrix has a very specific form. The rows come from the expressions, or the rows of the expression matrix, and the columns come from the columns, or the set of inputs, from the input matrix. So when we have two matrices, let's think about this for a minute. This matrix, let's think about it as being 2 rows by 3 columns. This one, let's think of it as being 3 rows by 2 columns. Notice that if we pick these outer numbers, this 2 and this 2, that's the size of the output. Because the rows here turn into rows here, and the columns here turn into columns here. These other guys must match each other. And let's think about why. 3 columns here represent 3 variables. 3 rows here represent 3 variables. In order for this input operation to be well defined, we need those 2 things to be the same, because we need to be plugging in the same, we need to have information for the same number of variables as there are variables in the expression. Hence, we can almost just kind of cross that out and say, hey, look, the size of the output matrix is simply going to be a 2 by 2 matrix. Thanks for watching.